In this video, we will discuss exponential functions as mathematical models. Many problems arising from practical situations can be described mathematically in terms of exponential functions or functions closely related to the exponential function. As you know, the exponential function f of x equals b of x is an increasing function when b is greater than 1. In particular, the function f of x equals e to the x has this property. Suppose that q of t represents a quantity at time t. Then one may deduce that the function q of t equals q0 or q naught e times e to the kt, where q naught and k are positive constants, has the following properties. Q of 0 equals q naught, and q of t increases rapidly without bound as t increases without bound. Since q of t is greater than 0, because q naught is assumed to be positive, and k is greater than 0, we see that q prime of t is greater than 0. So q of t is an increasing function of t. Additionally, the rate of increase of q of t is proportional to the amount q of t of the quantity present at time t. That is, as time passes, not only does the quantity increase, but the rate at which the quantity increases is also increasing. The exponential function q of t equals q naught times e to the kt for 0 less than or equal to t less than infinity provides us with a mathematical model of exponential growth, where k, the constant of proportionality, is called the growth constant. For example, under ideal laboratory conditions, the number of bacteria in a culture grows in accordance with the law q of t equals q naught e to the kt, where q naught is the number of bacteria initially present in the culture. K is a constant determined by the strain of bacteria under consideration and other factors, and t is the elapsed time measured in hours. Suppose 10,000 bacteria are initially present in the culture and 60,000 present 2 hours later. How many bacteria will there be in the culture at the end of 4 hours? We are given that q of 0 equals q naught equals 10,000. So q of t equals 10,000 e to the kt. Next, the fact that 60,000 bacteria are present 2 hours later translates into q of 2 equals 60,000. Thus, 60,000 equals 10,000 times e to the 2t, and thus e to the 2t is equal to 6. Taking the natural logarithm on both sides of the equation, we obtain 2k equals the natural log of 6, so k equals the natural log of 6 divided by 2, which is about 0.8959. The number of bacteria present at any given time t is given by q of t equals 10,000 times e to the 0.8959t. In particular, the number of bacteria present at the end of 4 hours is q of 4 equals 10,000 e to the 0.8959 times 4, which is about 360,000. Note that this is only an approximation because we are using a decimal approximation of the value of k. If we used k equals the natural log of 6 over 2, the value returned will be exactly 360,000. B. What is the rate of growth of the population after 4 hours? To find the rate of growth, we take the derivative q prime of t equals 10,000 times e to the 0.8959t times the derivative of 0.8959t, which is 10,000 times e to the 0.8959t times 0.8959, or 0.8959 times q of t. Using this shortcut makes it easy to find the rate of change. Since q of 4 equals 360,000, q prime of 4 is 0.8959 times q of 4, which is equal to 0.8959 times 360,000, or 322,524. The book rounds this to 322,500, but we can be more exact than that. At any rate, the rate of growth is approximately 322,500 bacteria per hour. In contrast to exponential growth, a quantity exhibits exponential decay if it decreases at a rate that is directly proportional to its size. Such a quantity may be described by the exponential function q of t equals q naught times e to the negative kt, where 0 is less than or equal to t is less than infinity, where the positive constant q of q naught measures the amount present initially, t equals 0, and k is some suitable positive number called the decay constant. The choice of this number is determined by the nature of the substance under consideration and other factors. To verify the properties of the function q of t, we compute q of 0 equals q naught times e to the 0 equals q naught, and q prime of t equals the derivative of q naught times e to the negative kt, which is q naught times the derivative of e to the negative kt, which is negative k times q naught times e to the negative kt, or negative k times q of t. Note that the derivative is always negative since q of t is always positive, and thus q of t is always decreasing. Radioactive substances decay exponentially. For example, the amount of radium present at any time t obeys the law q of t equals q naught times e to the negative kt, where q naught is the initial amount present and k is a specific positive constant. The half-life of a radioactive substance is the time required for a given amount to be reduced by 1/2. It is known that the half-life of radium is approximately 1600 years. Suppose initially there are 200 milligrams of pure radium. Find the amount left after t years. The initial amount of radium present is 200 milligrams, so q of 0 equals q naught equals 200. Thus, q of t equals 200 e to the negative kt. Next, since the half-life of radium is 1600 years, we know that q of 1600 is 100. Thus, 100 equals 200 times e to the negative 1600k. So e to the negative 1600k equals 1/2. Negative 1600k equals the natural log of 1/2, which is negative natural log of 2. And k equals the natural log of 2 over 1600, which is about 0.004332. So the amount of radium left after t years is q of t equals 200 e to the negative 0.004332 t. What is the amount left after 800 years? The amount of radium left after 800 years is q of 800, which is equal to 200 times e to the negative 0.004332 times 800, which is about 141.42, or approximately 141 milligrams. How fast is the amount of radium changing after t years? Recall that in exponential decay problems, q prime of t equals k times q of t. Therefore, the rate of change of the amount of radium present after t years is given by q prime of t equals the derivative of 200 times e to the negative 0.004332 t, or 0.04332 times 200 e to the negative 0.004332 t, which is equal to negative 0.08664 times e to the negative 0.004332 t. Finally, how fast is the amount of radium changing after 800 years? After 800 years, the amount of radium present is changing at the rate of q prime of 800, which is about negative 0.06126. So it is decreasing at the rate of approximately 0.06126, about 6/100ths of a milligram per year. We can apply the exponential function to describe certain types of learning processes. Consider the function q of t equals c minus ae to the negative kt, where c, a, and k are positive constants. To sketch the graph of the function q, observe that its y-intercept is given by q of 0 equals c minus a. Next, we compute q prime of t equals k times ae to the negative kt. Since both k and a are positive, we see that q prime of t is greater than 0 for all values of t. Thus, Q of t is an increasing function of t. Also, the limit as t approaches infinity of Q of t is equal to the limit as t approaches infinity of c minus ae to the negative kt, which is the limit as t approaches infinity of c minus the limit as t approaches infinity of ae to the negative kt, which is equal to c. So y equals c is a horizontal asymptote of q. In the graph, the part corresponding to negative values of t is drawn in gray, since in practice, one normally restricts the domain of the function to the interval from 0 to infinity. Observe that starting at t equals 0, Q of t increases rather rapidly, but then this rate of increase slows down considerably after a while. We can see this by calculating the limit as t approaches infinity of Q prime of t equals the limit as t approaches infinity of k times ae to the negative kt, which is 0. This behavior of the graph closely resembles the learning pattern experienced by workers engaged in highly repetitive work. Because of this characteristic, the graph of the function Q of t equals c minus ae to the negative kt is often called a learning curve. The camera division of Eastman Optical produces a 35mm single lens reflex camera. Eastman's training department determines that after completing the basic training program, a new previously inexperienced employee will be able to assemble Q of t equals 50 minus 30e to the negative 0.5t Model F cameras per day, t months after the employee starts work on the assembly line. How many Model F cameras can a new employee assemble per day after basic training? The number of Model F cameras a new employee can assemble is given by Q of 0 equals 50 minus 30 equals 20. B, how many Model F cameras can an employee with 1 month of experience assemble per day? How about 2 or 6 months of experience? The number of Model F cameras that an employee with 1, 2, and 6 months of experience can assemble per day is given by Q of 1 is about 31.8, Q of 2 is about 38.86, and Q of 3 is about 48.51, or approximately 32, 39, and 49 respectively. How many Model F cameras can the average experienced employee ultimately be able to assemble per day? Since the limit as t approaches infinity of 30e to the negative 0.5t equals 0, the average experienced employee can ultimately be expected to assemble 50 Model F cameras per day. We're going to pause here and continue in the next video.